It's been a while since the OSI lecture. Do you remember what the role of the data link layer is? That's right, next hop delivery, but isn't that what the file layer did as well? So both the physical layer as well as the data link layer provide next hop delivery, but the physical layer does bit by bit delivery, whereas the data link layer does frame by frame delivery. Frame is just a block of data. Remember encapsulation, where the network layer passes some data to the link layer. We call this the payload, and the link layer is going to add a header to it. And this whole thing, the combination of header and payload, is a frame. So the data link layer uses the services of the physical layer to deliver the frames. That is, frame is nothing but a bunch of bits. So the data link layer delivers the frame to the physical layer, which will convert the bits into signals and delivers it to the other node. And this physical layer here is going to convert the signals back into bits and passes them up to the data link layer, which reassembles the frames. So basically the physical layer is used as a building block to deliver frames at the data link layer. Great, but if frame is just a bunch of bits and we have already covered bit by bit delivery at the physical layer, what is left to do at the data link layer? There is plenty. So before I get into that, let me mention a few things. So the link could be a point-to-point link, in which case only two nodes are attached to the link, or it could be a broadcast link, in which case many nodes are attached to the link. In this case, they tap into the link to get the signals. Example, wireless is a broadcast channel. So when you transmit, anyone in the vicinity can receive that particular packet. At the physical layer, whether a link is point-to-point or broadcast really doesn't make that much of a difference, because as the signals propagate, each of these nodes, whether it's point-to-point or broadcast, are going to tap into the link to get the signal. Whereas at the data link layer, it matters whether a link is point-to-point or broadcast. Why? We will cover shortly. Remember what protocols do? So basically, link layer protocols define the format of frames that are to be exchanged over the link, as well as the action to be taken by the nodes when they send or receive these frames. There are a lot of link layer protocols: Ethernet, token ring, Wi-Fi, PPP, so on and so forth. So as part of this course, we are going to cover a few of these protocols. As promised, there is a lot of action at the link layer. The link layer itself is divided into two sublayers. LLC stands for Logic Link Control, and MAC, it stands for Media Access Control. So the Logic Link Control interfaces between the network layer and the MAC sublayer. Its main job is basically multiplexing. We covered this before. What is it? So when a link layer receives a frame, it needs to determine which of the higher layer protocols it needs to pass the payload to. So that is demultiplexing, which is part of multiplexing. Another job that the link layer does is error detection. We'll again cover this in detail. Optionally, it can also do error recovery as well as flow control. It's optional because not all link layer protocols employ these two. So for example, Ethernet doesn't do error recovery or flow control, whereas some of the wireless protocols do these. Media access control, as the name suggests, controls access to the physical media. This is mainly applicable in broadcast channels where there are many nodes attached to a link. Why do you think we need to control access to the media? That is, decide who transmits when on this particular physical media. Is it okay if two nodes transmit simultaneously? What's going to happen? So that's right, packets will collide, which will result in errors and wastage of resources. So framing is a functionality which at times is implemented as part of the MAC, at times as part of the LLC. It doesn't really matter where it is implemented. We are anyway going to look at framing in detail as part of this video. Another functionality that is implemented at the link layer is switching. Basically, this permits interconnection of local area networks. So that is what LAN stands for. Again, if things are not clear, don't worry. We are going to cover a lot of these things as part of this course. Framing. So what's the problem here? A frame is nothing but a block of data, basically a bunch of bits, and these frames could be sent back to back over the link. So the problem here is, how do you determine which sets of bits constitute a frame? So in writing, how do you separate out the words? You use spaces, right? A gap between two words. So can you do something similar here? So the space gap in writing translates to a time gap here, that is basically keep the link idle between two frames. Unfortunately, this cannot be used. Any ideas as to why? Yeah, this is a tough question. Unfortunately, this produces a dependence on the file layer. Remember the OSI principle? You basically don't want such dependence. You want to keep the design modular. In other words, the link layer should work with any file. It shouldn't matter how the file is designed. So for example, some file layer encodings may use idle time to encode data. For example, in unipolar, you have something like this. So 0 is encoded as an idle time and 1 is encoded as a voltage level. Now, if you want to use idle gap, this encoding cannot be used. Now, similarly, some other file layers don't keep the link idle. In other words, they continuously send data to maintain synchronization between the nodes. So in other words, if you want to use this approach to separate frames, then you cannot use some of these encodings. So if you want to use these encodings, you need to come up with some other approach. So can you think of another approach? Here is a hint, bookmarks. So you could use a marker at the beginning and end of your frame to show that this is the beginning and end of the frame. So this marker approach is called a sentinel approach at the data link layer. And this marker is either a special character or a bit sequence. So at times, instead of using an end of frame marker, you use a byte count. So you do something like this. So this byte count specifies the length of the frame. So after the marker, you interpret the byte count and then you count the bytes and then you know that this is the end of the frame. So based on this concept, there are two approaches to framing. One is the byte-oriented protocols, which view a frame as a collection of bytes, not bits. So this is one of the older approaches to framings. Basically, this was used to connect terminals to mainframes and their characters were extensively used. So in this approach, a special byte acts as the sentinel, and these are examples of some of the byte-oriented protocols: BYSYNC, DDCMP, PPP. So here you can see the frames. So in the BYSYNC protocol, a lot of sentinels are used to indicate several things. So the sync is used to indicate the start of the frame. Start of header is used to indicate the start of the header. Start of text is used to indicate the start of the body, which is the payload, and end of text is used to indicate the end of this particular body. CRC stands for cyclic redundancy check. This is part of error detection, which we'll cover later. A thing to note here is the sync byte is specifically chosen to produce enough transitions so that you can synchronize between the sender and the receiver. This is for recovery of the clock, as we covered as part of the encoding. So BYSYNC uses a lot of sentinels. This is really not necessary. As you can see in the PPP protocol, all you used is a beginning sentinel and a end sentinel. In between is the payload plus header of the PPP. Similarly, the DDCMP uses a sentinel for marking the beginning of the frame, and then it uses a byte counting approach to mark the end of the frame. So that's with byte-oriented protocols. So in bit-oriented protocols, a frame is viewed as a collection of bits, and these bits could come from ASCII character set or pixel value or from a binary file. In other words, these bits don't have to respect a byte boundary. So here is an example of a bit-oriented protocol, HDLC. It stands for High Level Data Link Control, where the sequence is used as a sentinel to mark the beginning and the end of that particular frame. So within here you have the header, the body, and the error detection CRC. So are we done with framing? Nope. There is a problem with using a sentinel to mark the beginning and end of a frame. What do you think this problem is? Think carefully, it's not that difficult. So here is the problem. What if the sentinel character, example the ETX or this ending sequence, appears in the body? In this case, you will think that the frame has ended when it has not ended and you're going to terminate the frame. So this is going to result in errors and you don't want this. So any ideas on how to overcome this? Basically, you don't want this pattern, either the character or the sequence, to appear as part of the payload. So here is a hint. If you know C language, how do you think a quotation mark that occurs in a string is handled? So one approach is byte or character stuffing. This is used in byte-oriented protocols. So what is basically done is if a sentinel character appears as part of the payload, you're going to precede it with a DLE. For example, if ETX is part of the payload, so this is the payload, so you have STX here and it is ending with the ETX, and this ETX has appeared in the middle of the frame. Now what you instead send is you send DLE ETX instead of ETX. So there is some other stuff preceding it, and this is the beginning and this is the end. Now the DLE character itself is escaped by another DLE character. Why do you think this is done? So if this DLE character appears at the end of the payload, there will be a problem. As you can see, that you would think that this DLE is escaping the ETX, which indeed is the end of the frame, which is not the case. So you need to escape this DLE with another DLE. So here is what happens. So if you have DLE ETX as part of the payload, sorry, this is ETX as part of the payload, what you are going to send is DLE, 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 ETX. So this DLE is escaping this DLE, this DLE is escaping the ETX. So the other approach that is used in the bit-oriented protocols is bit stuffing. So for example, if the flag were this, so what you do is that if this flag were to appear in the body of the message, you basically do the following. The sender inserts a 0 after 5 consecutive ones, and the receiver removes the 0 that follow 5 consecutive ones. So basically by doing this, you are ensuring that 6 consecutive ones never appear in the body of the message. So that way the flag itself doesn't appear as part of the body. So for example, if this is the pattern that is there as part of the body, by the way, this is not the flag, still the sender after the 5 ones is going to insert a 0, and this is what is going to be transmitted. The receiver, after it sees the 5 ones, it is going to remove the 0 and pass this up. Now here is a question for you. What do you think the receiver should conclude when it sees this pattern as part of the bit stream that it is receiving? That's right, it has to conclude that an error has happened because this cannot be part of the payload, because 5 ones should be followed by 0 if it were part of the payload, and this is not even a flag. So something has gone wrong. So now we are done with frame. So here is a quick summary. As part of the data link layer, we looked at the various services offered by this layer, basically the framing, multiplexing, error detection, media access control, and so on and so forth. We looked at one specific aspect, that of framing, how to detect the beginning and end of frames. As a solution to this, we considered the Sentinel approach, and here we looked at byte and bit-oriented protocols. And there was a problem with the Sentinel approach, and which we overcame by using byte and bit stuffing. Next, we will look at other services offered by the data link layer.